Quer dizer,
Hello. Well, let us start this session. I would like to thank all of you that are here. And this is a very special session in honor of 70 years of Professor Constantino Tsallis. This session is divided in 3 parts. In the first part, he will receive a plaque because now he's Emeritus Professor of CBPF. And the second part, Professor Coniglio will say some words. And then the third part, Constantino will give a small seminar. Unusual thing. So let us start. Constantino is now an Emeritus Professor of CBPF, and I invite Professor Freire, the Director of CBPF, to give him the commemorative plaque.
Good afternoon. My name is Fernando L. I'm the pleasure to be the Director of CBPF today. And I will give you a brief introduction about how one can be emeritus of CBPF. CBPF is divided in different sections. It's the theoretical division, the it's not an ice cream, so ice cream medication. Well, the CBPF is divided into many divisions: experimental or applied physics, high energy physics, theoretical physics, and the division must submit the proposal to our internal council that is composed by the different heads of this division, some members elected by the community of CBPF, and if approved by the council, the proposal submitted to the Technical and Scientific Council of CBPF that is composed by members from CBPF and also from the scientific and academic community of Brazil. For example, the president of the Nuclear Commission, the Brazilian Nuclear Commission, the scientific director of FAPERJ, the founding agents of the state of Rio de Janeiro, the director of the Leite Synchrotron Laboratory, and they have the final decision. The appointment of Professor Tsallis was unanimous in both levels, and it's a pleasure to me to give you a small.
thank you very much. In your name, I thank all those committees that you mentioned. And well, they say that when you become emeritus, you have to make less reports, you have to participate in less committees, and all this fills me with great joy. So, thank you very much again.
Well, thanks to the Director of CBPF. And now we are going to the second part, Professor Coniglio from University of Naples.
It's really a great honor to introduce Constantino's special talk on the occasion of his 70th birthday. Constantino was born 70 years ago in Athens, as everybody knows. Unfortunately, I don't have a picture of this special event, but I have some other pictures which has been provided by Fernando, and so I will say these few words around these pictures. So this is Constantino when he was 3 years old with his father. Later, you see with the rest of the family, the mother and the brother and sister. This is 1951. And this is really, I like it very much. It's so cute. But you're still cute, you know? I met Constantino much later, not when he was so young. And in fact, it was in 1970. I think I showed already this picture. This was in Varenna. Not everybody was here, so I will show it again. This is a summer school in Varenna in 1970, and you see where Constantino is. Constantino is here. Right? Nobody will recognize him. And I am next to him here. It was completed by accident. But somehow there was some kind of attraction. Because at that time we didn't know each other. And I think that Constantino was on his way, if I am not mistaken, on to Paris. That was the year when you started your PhD in Orsay. Correct? And in fact, he stayed there for 4 years, and in 1974 he got a PhD in Paris, at the University of Paris. So you came from Paris, that's why I didn't know whether you came from Paris to Bahrain and then back to Bahrain, or directly from, so you came from Paris. Very good. So I, for most 10 years, I was very sad because I never saw Constantino in these years. But I met again him at the beginning of the 80s, 1981, maybe 1982, in Boston University, where we met, and there was immediate nice friendship. We wrote a couple of papers studying them with Cedar Etner, well, on the break collapse method. That's a method very famous that was presented and was developed by Constantino in order to do very efficient calculation on renormalization group. And after that, we again, since there was this sympathy, we immediately thought we had to meet again. So what we did was to write a proposal between CNR and CBPF, and we wrote the proposal, we got the grant, and so I managed to come to CBPF just here. It was 1983. And this was a wonderful atmosphere, I must say. It was beautiful. There were lots of students around. a lot of visitors, and so I had the occasion to meet these people, not this is 2007, but they are the same people. There is Aglaé, Fernando, Evaldo, Ananias, who were at the time students here. Now they are much older, but I remember they were kids at the time. And there are some more here. There is Luciano, Conceição, again Ananias, Anna, and Pinheiro. So I like the atmosphere very much, in particular this feeling between Constantino and his students. I like the way they interacted. Constantino, you know, is brilliant, always volcano, full of ideas. So at some point he has an idea, has an intuition, whatever. So he's writing a formula, writing something. As you have seen already in this meeting, you just say, you should put this way. And that's the same he did with the student. He told the problem, he said, it should be like, the solution should be this one. And then let the students go home. Maybe it took some time, maybe a month, 2 months. But eventually he came back with the solution. The solution was what Constantino predicted. In fact, I remember that once one of the students, a joke, said, but what's the point to go and check it? I mean, we spend a lot of time, we could go to the beach. If Constantino said so, it must be true. And myself, I had the opportunity in order to check his intuition, the way he really sees things. I don't know how he does. Maybe he will tell eventually the secret. Because he sees and then he sees the solution. And this happens when I was CBPF, and at the time we started to discuss fractal structure of proteins. I was discussing with Hellman, remember, nice guy from Mexico, a scientist, from Argentina, in Mexico, okay. And we were discussing essentially the anomalous behavior of the relaxation time of a protein. And we were trying to understand why this anomalous behavior. The protein usually supposed to be a kind of like a self-avoiding walk, like a string. And this model did not work. So we said, well, maybe this is not a good model, we should put some bridges. No? So we changed the model from the self-avoiding walk to the self-avoiding walk with the bridges. And at this point, what we need to do, what we need to know was what would be the fractal dimension of a random walk on such a structure. We didn't know the fractal dimension of the structure, so we didn't know the fractal dimension of the walk. And I remember talking to Herman, we were stuck. I remember in the room, we were stuck in the room discussing. At some point, ta-da, Constantino comes in the room. Deus ex machina, no? And he said, what's going on? And so we told him the problem, and they say, we don't know how to go on. We are stuck, because we don't know the fractal dimension of this structure. We don't know the fractal dimension of the walk. And he started to think, ask some question, Antonio, what is the fractal dimension of this and that? Then he thinks. Then, ta-da, here comes, he goes to the blackboard and draws these two lines. One line is the fractal dimension of the random walk for the protein without the bridges, and this other one, this horizontal one, I remember vividly, this line, this is the fractal dimension of the random walk on the protein, whatever, and this is constant. Doesn't matter what the fractal dimension of the structure is. In fact, this was the solution. I mean, we were astonished, but oh my God. But because at this point, we know the fractal dimension of the walk independently on the protein. And so that was the basic part. And happened that this was, in fact, the solution of the problem. And we immediately wrote a paper, sent to physical regulators, was approved, was accepted, and had a huge success. I mean, it was a lot of citation, a couple of comments. So it was really good. But just to see, comes Constantino, draws two lines, geometric and very neat, and that was the solution. So I still remember this was, for me, a shock. I mean, to say this is really a special person. At the time, we did not have only scientific interactions, but there was also, let's say, a close friendship. So he invited me to his house, to his family, and this was the family at the time, in 1984, actually when I was there. And you see with Christina, who is here, and Alexandra, who's also here, and Adria, who's also here. And for me to see, I remember, I saw the before, I mean, I couldn't recognize him because I remember him so little. In fact, I remember with him that every time we spent lots of evening together, and I used to go away, and he said, Antonio, cuidado stare mulatas. You remember that? I still don't know why you said this.
He followed his own advice.
I don't know, it must have been Constantino who told him strange stories about me. So it was a really great time at the time, and I really appreciate very much this kind of affection, this kind of feelings that it was built between me and the rest of the family. Later on, I also had the chance to meet the second son, which is Emmanuel, and we also had a lot of, who is? Hey! Emmanuel, remember? We also had a lot of fun together with Emmanuel when I happened that I met him. So, Constantino has been away with his children. He likes his children, and in fact, here is Constantino with all his children, and they are having fun. It seems they are still celebrating Father's Day. These funny hearts, everything is so clear. But I think that at this point, with those his funny heart, he lost authority on his children. How can you feel respect for a father with all these funny hats? So he said, well, I have to gain authority again. And so what I do, okay, this is I need to change this look from the guy with the funny hat, and in order to gain respect, I mean, he became commendador. So this is Constantino in the suit of commendador. And it was not just a suit, I mean, it was real. Here is when we received the award of commendador, the Orden Nacional de Mérito Científico, and I think also there is
President Lula is.
there is Lula, that's right, yeah. So it's real, it's that's to show it was not just a joke. I mean, so when he went back home, he really gained respect with his children. But Constantino had so huge reputation that he received many more prizes and recognition. This is, in fact, he got this Mexico Prize for Science and Technology, and from President Fox. And again, here is Constantino being awarded of Aristio, which is this award by the Academy of Athens in Greece. This modern Academy of Athens has its origin in the academy founded by Plato in the 5th century before Christ. So it's very important, it's really amazing. Here is when he received the Esseger Prize for the importance of his scientific production. And again, this is when Constantino received the title of Doctor Honoris Causa by the Aristotelian University of Thessaloniki, Greece. And then he received many more of this Doctor Honoris Causa. This is another one from the University of Cordoba, Argentina. And again, another one from the Estate de Maringa. And here, I mean, it's not esagerato. From Natal. And this is the But so apart from frequenting people like Mickey Mouse, Constantino also collaborated and interacted with high prestigious people. Here is with Andrea Capisalta, who is here, and Eddie Cohen in Cagliari. It looks like as if David, right? You can notice that his bottle of wine is completely empty, but seems they still manage to go on. Later on, you see, because Andrea completed his house. And see, the red wine is finished, so the two people seem to have said, I don't know what happens afterwards. And also, he was, with this case, with the Nobel laureate, Gerardo Tuff, in Rio de Janeiro. And I think this was in Santa Fe with another Nobel laureate, German. And this is what I think he was saying. See, you know what you say, but it looks like it for sure, but with an actor. It looks like that's what is the impression. Okay, now it's Boltzmann and Tsallis. It's the day we had the language discussion. There is some kind of I don't know if they hate or love, but there is definitely a kind of mixed feelings of competition and appreciation between these two guys. Many people say, in fact, that there are a lot of similarity between Boltzmann and Tsallis. They both gave important contribution to the fundamentals of statistical mechanics. Both had many followers and many opponents also.
The only difference is the beard.
The beards. In fact, I must say I don't agree. I don't think that they are very similar to each other. This is our friend Boltzmann, the father of extensive statistical mechanics. And here is the father of expansive statistical mechanics. Now, what, do you think there is something in common between these two? I don't think so. Now, let me just to close, to show some typical Constantino's look. This is this is a romantic look of Constantino. He is very professional. Smart. Wise. That's what we like. Happy birthday, Constantino, with the, the languages and many flowers. Now, it's not finished yet. So. Now there is a video, sorry, there is a video with messages from many friends around the world, and it's going to go on. Okay,
Well, let us thank Coniglio, this very, really wonderful speech. Now we ask Andrade, né? The Andrade showing his talk is movie time.
Okay, move it.
John Marsh here at the SUNY Institute of Technology in upstate New York, wishing Constantino a happy birthday on his 70th. Congratulations.
Hello, Constantino. This is Christian Beck from Queen Mary, University of London. I wish you a fantastic birthday and have a great time over there in Rio. And instead of doing long speeches, I want to do a little bit of Q statistics for your name. So I illustrate that here. I've written your name here on this blackboard, and since you're very often adding little indices Q to formulas, I did that here for your name as well. And then let me, this is a slash here, so make a longer slash here. And also I might put, for symmetry reasons, a slash here. And perhaps also here. So let's see what we got. Well, maybe I take that here as one word, like that. Okay, we got S, not constant. Well, that's precisely what you're doing. It's not equilibrium, right? Yes, it's not constant. And what do we do then in non-equilibrium? Well, it says all is Q. That's your solution indeed, Constantino. Well done. Okay, and with this little sketch, I finish here. Have a great time.
Hello, Constantino. Hello, everybody. Obviously, I'm not with you. But I'm so much thinking about all of you and this wonderful meeting, which will be one that I will regret not to have attended. So many interesting talks, so many interesting topics, so many interesting researchers. And most of all, at an appropriate time for wishing Constantino a happy birthday. He is joining the selected club of Whiten researchers, the Whiten 70 guys. He's already Whiten, eh? Not yet 70. Catch me up soon, Constantino. Take care, and moreover, I don't want to forget your world recognition as a scientist and as a gentleman. Thus, not only I'm saying to you happy birthday, but also I say buon anniversaire, and feliz aniversario, and feliz cumpleaños, and Carmena Gentella. Take care, Constantino. We need you in a long time. Parabéns. Parabéns.
querido Constantino, gostaria de desejar a você feliz aniversário. Well, maybe I should switch to English since it's an international conference. My name is Maria Conceição. I did my PhD with Constantino years ago. We had a really enjoyable collaboration and I missed so much that time. I'm so sorry I cannot go to this conference, but for personal reasons it is not a good time for me to travel. But I want to wish you a happy birthday and I want to thank you for all you did to me. For my professional career, you helped me in some difficult moments of my personal life. And I really have nothing more to say than to thank you and happy birthday. And congratulations for the great career you are having and for all the contributions that you did for physics. And I hope you enjoyed the little gifts that I gave to you. I sent in the mail just the biography of Maria Callas and a set of 6 CDs with their recording. I myself have those CDs and I love them. I love opera. So enjoy, and I hope this conference that you are having for the celebration of your birthday will be a big success. Bye.
Buen dia, Constantino. This is Gene, Boston. I'm so honored to be invited to say something at your big birthday event. And I'm so sad that I cannot be there. That's one reason I called you last night, on the very day of your birthday. So what am I going to say in 1 minute? Considering we have been friends for 43 years, since 1970, when you came as a 27-year-old student to Verona, Lake Como. And at that time I met you. Your picture is next to Coniglio in the upper right corner. And of course you don't look like yourself at all, and nor does Coniglio. You two are also the best of friends. And the wonderful message for all the young people in this meeting is that in science you can make a friend in your youth and keep close to that friend all your life. We've never had a single quarrel in our entire 43-year relation. And our friendship got really deep a few years later when you invited me with my wife and my 2-year-old son and my brand new baby daughter to Rio in January 1980. And there you took such good care of us, including bringing the entire family to a rehearsal of Mangueira. Mangueira, for those who don't know, is a samba group. And the meeting was in January, which you know is just before Carnival, so they were rehearsing. And the most dramatic thing, which everyone always remembers, is that these beautiful woman came over, wearing almost nothing, and looked at all of us, and then didn't choose you or me, but chose my 2-year-old son. He came up and started dancing with him on the floor. And everybody was very jealous, everybody was unhappy, including him. He did that with when he was only 2. And he learned and I hope you will come to Boston again. You're welcome here at any time. Have a great party. Bye-bye.
Dear Constantino, how many times every day we pronounce your name? Many, I tell you. And this already since our first contact, when you and I realized that our work on non-Australian distribution in 1993 was in line with your proposed use statistics, and since your visit in Torino and in Cagliari, and since the early conferences organized in Sardinia in 2001, we deeply appreciate the fascinating time spent with you sharing researches in the well-known and respected but heretical for somebody else non-extensive statistical mechanics. From Giorgio Canedakis, Andrea Lavagno, Alberto Rossani, Antonio Maria Scarponi, and from Massimo Corazzo, Marcello Ischia, Giuseppe Mesorani, and from me, Piero, with warm heart. We send our happy birthday, Constantino.
Parabéns, Constantino. Let me first say that I am extremely sorry not being able to be present here to congratulate Constantino with his 70th birthday and give personally my appreciation of Constantino as a human being and as a scientist. In my opinion, and not only mine, but also of Murray Gell-Mann, Constantino has made a simple yet very ingenious and fruitful generalization of the basic Boltzmann-Gibbs measure, widely applicable to many new classes of interesting systems. He has achieved this through determined efforts and perseverance, in spite of much criticism. For all that, I greatly admire him, and I also sympathize with him, knowing firsthand that new creative and original ideas are often not appreciated by hoi polloi. Let me end by wishing him a continuation of his creative work to the benefit of physics and all of us working in that or related fields of science.
Well, this movie was made by doctoral student, PhD student of CBPF, mainly Leonardo Cirto.
Give a stop.
Ah, it's not stopped yet.
No, he's starting again. He's starting again. Give a stop.
Start again.
Okay, let's see.
So you see that the students here have other skills in physics. So, well, the third part of this session. So as usual, Constantino will give us a small talk, a short talk. So Constantino, please.
Really, it's very hard to find what to say for six. Hello? I was saying it's very hard to find words to express everything that I have witnessed in the meeting, but very especially in this session, starting with that honor by CBPF Director, and then all these things that Antonio has told you. I have many things to say about him also. I don't know if I should say them. Shall I? No. We were analyzing life with Antonio in several occasions, all the time. And at the end, we arrived to a big conclusion, that in life ce ne sono le donne, la fisica e il resto. This is an opinion that he shares. Maybe he created that hierarchy. everything that I read here and everything that was done, I appreciate enormously. I know that to organize this, it has been a tremendous work, and I have to especially thank the organizers, Evaldo, Fernando, Roberto Andrade from Salvador, Andrés Souza from Aracaju, and on the infrastructure, Claudia, Betty, Almerio. But they have all of them worked a lot, and I am absolutely grateful to them. But I wanted to say here that there are two people that have worked like crazy, and to them I have no words for thanking. And that's Leo Sirto, where is he? He's not here? Yeah, Leo Sirto, and Fernando Nobre. They have dedicated a tremendous effort. Every day I was seeing them doing things in the computer with Claudia, secretarial things, writing to people. It's really something very, very touching, because I know that Fernando and Leo, as all of us, they have 1 million of things to do, and they left all this in lower priority just to do this work. Also, your presence here is perhaps the best gift somebody can receive. And also, it came to my mind while seeing all this, that all activities, all human activities, all the works, all the professions, can be very important. For example, cleaning the floor can be extremely important. Nobody would like to work or to live in a space which is dirty. Solving problems in the elevator, it can be also very important. So all works have important issues, but there are 3 activities that I consider myself very privileged. And those 3 activities are science, art, and sports. In these 3 activities, all human beings identify themselves. And I consider myself a big, big privilege to be in one of these 3 classes. In fact, I would like to repeat what I said some years ago in a meeting in Rimini, and I think I was referring to something that was going to happen in Turkey, that we scientists, artists, and sport people have a very special responsibility for humankind, because we can show them, we must show to all the others, that people with different countries, different cultures, different colors, they can collaborate, they can do things together, they can become friends, and at the bottom line, they can make life more pleasant for everybody. So I know here practically all or many of you are scientists, although there are some that are in different branches, like Alexandra, Maria Cristina, Marisa, Emmanuel, he's preparing his entrance to the university, Adrian, he's not exactly a scientist, he's an engineer, so all those activities are fantastic, but I know here most people are scientists. So I think we should feel very, very happy to have the possibility of giving such contributions to humankind that I was referring to. So, from the bottom of my heart, thank you very much. So I prepared here a short talk, right? So theoretical physics, crossroads, carrefour of truth and beauty. And I would like to dedicate this talk to my father and mother, Emmanuel and Cleopatra, to my brother and sister, Demetrio and Thalia, to Maria Cristina, who gave me Alexandra and Adrian, who gave me Flora and Enzo, and Maria Aparecida, who gave me Emmanuel, and also to Marisa, here present. I would like to start with this. Beauty is truth, truth beauty. That is all we know and on earth and all we need to know from John Keats. I was visiting a cousin of mine in Holland, and she likes books, so there were plenty of books in the room. And then I took one, and it happened to be poems by John Keats. So I opened the book, and I read this. So I was so impressed that I never forgot. And I used that idea as the title of my presentation. This has to do, Evaldo told me, oh, you're going to quote Aristoteles. Yes, yes, I said, yes, I'm going to quote Aristoteles. So here you have. Aristoteles Dixit, this one. Poetry is more elevated and more philosophical than history. For poetry expresses the universal and history only the particular. History tells us the events as they happened, whereas poetry tells them as they could or should have happened. So I find this one of the most beautiful definitions of what I consider theoretical physics. It is like poetry. It describes the world as it could or should be, in opposition to history, which provides the facts. And from this and this, I chose that title. As it has been mentioned by Antonio, for a variety of reasons I have been involved, I have been interested, intrigued by several things during my scientific life, but there were two periods that were special. So I would like to say a few words about each of those two periods, and this is the first one. This is the time I was thinking about fidelity, and I will say what is that: percolation, Potts model, transmissivity, break collapse method, random resistors, which we did together, random magnetism, randomization group, and all that jazz. Antonio said that maybe you can tell us the secret, how you find the answer. Well, I will try to give a description of how it works, and sometimes you do find the answer. This story of fidelity is the following. I was lying in the hamac in our apartment in Osvaldo Cruz, and I was trying to figure out how to express that in the Ising model, when one spin is up, it provides information to the other one to be up also. And so there is, through that channel, there is information flowing. It can flow very well at low temperature. It can hardly flow at very high temperature. So I said, how to define this? And I was, resting in the hamac. And I said, I need something such that 80% of 30% is the equal as 30% of 80%. I wanted something that would commute. Because I say, if this channel loses some information, and the next one loses, it would be the same if it goes the other way around. First the other one loses information, and then this one. So I wanted something to be such that 30% of 80% would be the equal of 80% times 30%. And so I came to something, and I called it fidelity. How faithful is the connection to transport the information. But sometime later, I realized that that concept already existed, and it is the concept of probability, which appears in percolation. This story ended by providing a lot of papers, but I chose these two as being the essential ones. This is when the idea appeared, and this is when we finished this together with Aglaé. De Gennes once told me, if you want to understand a subject really, write a book on the subject. And he did that his entire life. Every time he wanted to know something, he wrote a book, and then he abandoned the subject and went to another subject until he wrote a new book. So that was the way of behaving of De Gennes. So I wrote these physics reports, and somehow I abandoned the subject. So somehow this was an important first step, and that was an important last step. But let me show to you how it worked. So here you have the probability of a series array, one after the other, and the probability, the equivalent probability of connecting this point to this point is this one to be present and that one to be present also. So the probability is P1, P2, and that's a series array of something through which information is flowing. This is an AND. But then you can have an OR with this, which is a basic parallel thing, in which information can arrive from here to here, flowing both ways, or this way and not the other one, or this way and not the other one, but they cannot be both of them close. Then it doesn't work. So the probability of this is both present, one present and the other one absent, the other one present and the other one absent. And that's it. They cannot be both absent, because then the information does not flow. So this gives you this little formula. And this is where beauty enters. I said, okay, this is the answer, but it is not beautifully written. It's true, but it's not yet beautiful. So I rearranged it, and P equal this can be rewritten like this. 1 minus P parallel equal 1 minus P times 1 minus P. So now it is beautiful. Why? Because here it has the same operation that it has here, a product, here, here. Here it has a functional form which is the same here and the same here. And then I say, now it is P. So let me call 1 minus P dual probability. So I define dual probability like this. So this formula becomes this. And now I say, this is really beautiful. It is terribly similar to series. So I am transforming the logic and into the logic of or, and both ways, to a very simple expression. You may say, well, okay, that's nice, but can you do science with that? Well, yes, you can. These operations here, so simple, can in fact give you the most compact proof that bone percolation in square lattice is 1/2, because you write this equal to its dual, which means this equal 1 minus PC, which means PC equal 1/2, which is the exact answer found by Sykes and Essen. And you will see how this follows. Then I became interested in the Q-state Potts model, whose Hamiltonian is that one. So there you have a capital Q. It used to be small q, but I put capital Q for not confusing with another Q that I'm going to talk in a while. So this is the basic Hamiltonian of a bone. And now I say I have two bones, this and this, in series. So seen from outside, it is the whole thing seen as one bone. And to have the preservation of correlations, you write here the Hamiltonian of this and this, which you see here with Boltzmann factor. Then you sum over the states of the central one. And whatever remains is how this is seen from outside. So the way a family is seen from outside is different from how it is seen by the elements of the family inside. But this is the view from the outside. And this becomes equal to that, with one bond, which is A to B. When you work out a little bit this, you can transform this into T series equal T1 times T2. And therefore we have the algorithm for series. Why this is beautiful? Because the concept is flow of information, and it has the same shape, like this. This is probability. This is a thermal thing, and they have the same shape. We are unifying. We are putting inside the ingredient whatever is necessary so that the ingredients behave in a universal way. And now, we have to give a name to this thing. So, there was a generalization of that concept of fidelity. So how to name this? So the idea is that it transmits information, well or not so well. So I was in the car with Robin Stinchcombe from Oxford University, and we are going in front of Clube Guanabara here, and I asked Robin how it sounds better for you, transmissivity or transmittivity? And he said, it sounds better, transmissivity. So I said, okay, so that's the name, thermal transmissivity. And this is how it has been used in many, many, many papers by our group and other people around the world. So this is series. Now what about parallel? When the information flows through here or through here, or. So the coupling constant is just the sum. But in this case, you say, okay, so leave it as it is, nothing more beautiful than a sum. But I will not leave it like that. I will transform this into the language of transmissivities, because I want to have in mind something like probabilities. So instead of writing this way, I will write this way. So this is the algorithm for the transmissivity of parallel array, which is blah, blah. This is nice for a variety of reasons. One of them, if you take q equal 2, this disappears, and this is 1 plus t1, t2. This is exactly the composition of velocities in special relativity. If t is velocity divided the velocity of light, Einstein showed that if the train is going to some velocity and you add to that the velocity of light, the whole thing does not go faster than light. Nothing goes faster than light. So it's useless to put more velocity if you have already the velocity of light. Useless to put an excellent, to put another channel if you have an excellent secretary here that never fails. So if the transmissivity here is 1, you don't need the other one. So you see the logic here is very similar to what happens in relativity. All these beauty, these connections, this richness are not here, but they appear here. So it's better here. Aristotle again, he said, metaphor, of all things the greatest, the only thing that you cannot learn from others. But so he said, metaphor is from all things the greatest. Metaphor means transportation in Greece. So this is a metaphor. We have here a thermal problem, but however the logic is very similar to special relativity. I find this beautiful. But then I say, okay, this is the parallel algorithm. It's not written in a beautiful way. So I play a little bit and I write it like this. This is the same as this, but this is more beautiful. Why? Because here it's a product, like here. And the functional form you have here is the same here and the same here. Now it is beautiful. Then this variable, let's put a name to that. T dual transmissivity. All this is dual transmissivity. And therefore this can be written like that. The same form that was here for dual probabilities. So everything is becoming unified. Whatever is not really essential to topology is put inside the variables themselves. And with this variable, you say, okay, it's nice, but so what? Well, it happens that if you write t equal t dual, you obtain the exact answer for the Potts model on the square lattice. I remember one day I had all this, and I wanted to know whether it had sense. And I had obtained this, and I wanted to know whether this was the exact answer. And I asked Evaldo, can you check in the literature what is the exact answer of the Potts model in square lattice? And one day after, he told me, I found it. It's exactly that. So I said, okay, it's working. From that dual variable, you can define a next variable, which is s, defined like this. Try to remember this formula, logarithm of 1 plus q minus 1 times t divided logarithm of q. With this definition of this variable, the dual s is 1 minus s. It's exactly the form of probabilities. So even better. We are putting various models of physics into a game which is basically the logic of and or. Very nice. From this, it appeared a method that was referred by Antonio, the brain collapse method, which are topological operations. And I knew this was correct, but I didn't know why. It happens all the time to me, to know something is like that, and I don't know why. Probably it happens to you many, many times. But one day, I had written a huge expression referring to this, the Wheatstone Bridge, in my blackboard. And Bonini, the professor from La Plata, who was working at that time here because the military dictatorship in Argentina put him away. So he was working here in Brazil. Here it was also a dictatorship, but softer than that of Argentina. And dictators are especially worried about the citizens of their country. The citizens of the other country are less important. So Bonini was here. And I had that huge expression in the blackboard, and he passed through the door like that with his head. He saw and he said, "Ah, a multilinear function." And then he went away. And then I said, "Oh, that's the reason. This is why this method works, because those are multilinear functions." And this is how I found it. Then to prove it mathematically, that's another business. Sapir knows about such things. It was proved, mathematically speaking, by John Essen at the King's College in London. But the whole thing was this mixture of what I consider beauty and that remark of Bonini crossing the door without knowing what were those variables. He didn't know anything. He just saw like that, oh, a multilinear function, and he went away. Let me now talk about the second period, which has to do non-additive entropies, non-extensive statistical mechanics, weak chaos, long-range interactions, generalized thermodynamics, Q-triplet, central limit theorems, nonlinear Fokker-Planck, black holes, and all that bossa nova. Why? Because jazz was born in the United States. And the first period, with all those critical phenomena, had a big influence in the United States. But this was born in Brazil. So it's not all that jazz, it's all that bossa nova. So here, I would like to quote Boltzmann. You said that I might have conflicting feelings about Boltzmann. Not at all. I have a big admiration with regard to Boltzmann. I consider him a genius. I have a poster of him behind me, and he hears me all the time saying, "This is not Boltzmann, blah, 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 blah," and he never said anything. So, I don't know if he likes me as much as I like him, but he does not dislike me. He never complains. So he wrote here in 1896, in his lessons of gas theory, the forces that two molecules impose one onto the other during an interaction can be completely arbitrary, only assuming that their sphere of action is very small compared to their mean free path. The sphere of action is very small, so it influences here. It does not influence far away. He says, only assuming that. He was assuming short-range interaction. You see why he was a genius. He invented statistical mechanics, and he had the intuition that it had to do with short-range interaction. This is in page 13 of his famous lessons on gas theory. And I wanted to show another one, that one from Ettore Majorana, who died at died or disappeared about 30 years ago, 30 years old. And of all a collection of things that I have with this, probably this of Majorana is the most precise, because somehow he distinguishes between additivity and extensivity. and all the others are confused. Fermi was confused. Most of them are confused. Somehow Majorana, in spite of being very young, he had a more clear idea about that. So he wrote, this is mainly because entropy is an additive quantity. In other words, the entropy of a system composed of several independent parts. Nobody says that. Fermi does not say that. Gibbs does not say that. Majorana says that. Independent parts is equal to the sum of the entropy of each single part. And then he says, one considers all possible internal determinations as equally probable. This is indeed a new hypothesis. He says, it's not God who told us. This is a new hypothesis. It might be different. And he says, we will therefore admit this as an extremely plausible working hypothesis whose far consequences could sometimes not be verified. Maybe it's not true that all configurations are equally probable. Could not be verified. Under this hypothesis, blah, 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 and comes Boltzmann-Gibbs statistical mechanics. Under this hypothesis. So let me go now to this table. On this line, you see Boltzmann-Gibbs entropy. There you have the famous minus sum P log P. When all probabilities are equal, this becomes logarithm of W, which is the famous formula which is in the grave of Boltzmann on the central cemetery of Vienna. And I went there, I took pictures, etc. And in that central cemetery on the left side, you have Mozart, Strauss, Father Strauss, son, you have all those, and on the right side you have Boltzmann. And this is why a professor of Vienna, whose name I will hide because Hans Hermann is here, he told me, you see, the central cemetery of Vienna has half of the population of Zurich, but it is the double funny. So this is in all books of physics, chemistry, mathematics, etc. But here you have an extra index, Q. So when in this you take Q equal 1, you go back here. So this is not an alternative to Boltzmann. It is a generalization of Boltzmann. It contains Boltzmann as the particular case Q equal 1. Why that? Because I might be a fool, but not completely stupid. So Boltzmann is working okay in hundreds of systems during 140 years. I'm not going to put this into garbage. This is a wonderful theory. So I don't want to replace it. I want to generalize it. But now, P log P can be generalized in 1 million different manners. Why this particular manner? This is a long story that I will not enter here, but these two expressions share a lot of important properties, like concavity, extensivity, etc., a whole bunch of things. Here you have a Mari that was mentioned today, and Topsoe, he appeared in one of the photographs. So they share a lot of things, but you must violate something here to generalize. Because the only thing that violates nothing is P log P, and you have not generalized. So if you want to generalize, you must violate something. So violations are not necessarily bad. They can be extremely good. So we need to violate something, but we want to violate in a Zen manner, just a little bit, the minimum possible, a minimalistic violation. We're going to violate additivity. This is additive, this is non-additive. Only that. And let us see what happens. when you violate the fifth postulate of Euclid with the point and the straight line and the parallel, when you violate that, you obtain Riemann geometries, Lobachevsky, Riemann, etc., a whole area of mathematics, and just by violating one important property. We are going to violate only one important property, additivity. So, let me tell you, and here we go back again to this thing of beauty. We shall define this function, q logarithm of x, like this. When q goes to 1, this becomes the normal logarithm, and the inverse function is the q exponential, which is this, and when q goes to 1, this becomes the exponential. With this function, the same table that you have here can be written in a more elegant way. Log, log, q log, q log. And the mathematician said, well represented, half solved. So if you do it nicely, in a beautiful manner, you have done 50% of the solution. So I will be referring a lot to q logarithm and q exponentials. And let me now give you the origin of this idea. And as most cases of if something in the foundations of physics, it is something terribly simple. So I was in Mexico City in 1985, and in the coffee break, everybody went outside, excepting me, who stayed in the room somewhere, who knows why, and it was in the blackboard, Edouard Brezin. Roger, where is Roger? Edouard Brezin was on the blackboard, and he was explaining multifractals to a Mexican student whose name I have not retained. I'd like to know who was that. Maybe Alberto can tell me one day who was that Mexican student. And Brezin was explaining something about multifractals to the student. And multifractals are plenty of p power q. So I was not hearing what they were saying because I was far away, but I was looking at the equations that Brezin was writing on the blackboard. And he wrote p power q, blah, blah, blah. Multifractals are plenty of p power q. And I saw that, I said, wow, with that we can generalize Boltzmann entropy, and therefore Boltzmann statistical mechanics. How come? Very, very simple. P is a number between 0 and 1. Say it's 0.8. If you put it to a power q below 1, it becomes bigger than p. You enhance the importance of the probability by putting a power smaller than 1. Square root of p is more important than p if q is below 1. The other way around if q is above 1. And it is equal if q equals 1. So this is a kind of aristocratic behavior. The minority controls. This is a kind of demagogic behavior. Majority controls, and the minorities are left out. And this is democracy, equal opportunity. Why that? And of course, this is Boltzmann. But why I wanted to change the role of probabilities? Because many of you have seen the motion of water, for example, in Iguazu Falls, and the water goes down like crazy. But there are some vortex there. They turn around, turn around. It's a hell of water, but those vortices do not care. They just turn around. So I say, it's impressive. Although this confusion, the vortices must be very important because they are always there. But a vortex is something with very, very small probability. A vortex is 1 trillion of molecules doing like this. The molecules here do not do that. The molecules here are doing like that. So to have 1 trillion of molecules doing this is very rare. It has a very low probability, and nevertheless is very important. We were speaking with Roger Black Swan. He likes Black Swan also. So very rare events that can be very important. So how a small probability can control things? By putting a power. Then it becomes big. This is why the power is called power in all languages. Potencia, power, puissance, in all the languages. The exponent is called power because it gives power to the variable. So how to put power on a very small number with something here which is very different from 1? That's the idea. You can say that that's terribly stupid. Okay, well, that's it. That's the idea. Because of that, when I was flying to Rio de Janeiro, I wrote down the entropy, SQ. It took me only 10 minutes, because once you have the idea of using P to the power Q, the rest is kind of trivial. Then, I went to Maceió. This happened in 1985. I went to Maceió in a meeting in 1987. And the organizer of that meeting was Enaldo Fonseca Sarmento. And he said, this afternoon there are no sessions, no talks. You just put in little groups there and you discuss whatever you want. And then I called Evaldo and Hans. And I said, come here. And we went to a room with a blackboard. And I told them, listen, I have a funny entropy there. Like that. I wrote it. It has this property. What do you think about that? And we were discussing like 40 minutes with Evaldo and Hans. Maybe this is this. We didn't know what it is, and I didn't know what it is. I only knew that it has P to the power Q, and I like that. So, now the importance of mosquitoes. When I went to the hotel, I was in a hotel which has not big air conditioning. And in Maceió, in the summer, there can be a lot of mosquitoes. So I was sleeping, and those mosquitoes. So that morning, I waked up, and I said to Enaldo, I am leaving Maceió. I can't support anymore those mosquitoes. So I took the airplane. I left the workshop a little bit before. I went to the airplane. I'm in the airplane because Hans and Evaldo were saying, yeah, it seems interesting, this thing. Maybe it has something to do with fractals, who knows. So I deduced, I made the optimization principle flying between Maceió and Rio de Janeiro, and I got the Q exponential. So I said, oh, how nice, a new function there. And when Q goes to 1, it becomes Boltzmann weight. Nice. So, in 1987, I had, for other reasons, the visit of the crème de la crème of statistical physics in Brazil in my office, and there was Salinas, there was Mauricio Coutinho. Who else was there? I think it was Sergio Coutinho and maybe, well, Cesar Sabarreto from Minas Gerais. He became the president of the Federal University. They were in my room. So after we finished our discussion, I told them, listen, stay there 10 minutes, I want to tell you something. So I wrote the entropy, but now I have also the stationary state distribution, which is the generalization of Boltzmann weight. So I wrote all this, and then I asked them, what do you think about that? I said, well, would you publish this on an international level, or just in the Brazilian Journal of Physics? And Salinas, he was the editor of the Brazilian Journal of Physics at that time, or at least the editor of statistical physics. And he said, oh, I will publish that on international level. But if you want to publish it in the Brazilian journal, it is already accepted. I had not written a paper, there was no paper. And he said, I accept it. So I wrote it and I sent it to the Journal of Statistical Physics. It was published, and little by little, 3 years later, with Evaldo, we succeeded doing the connection to thermodynamics. And 7 years later, we improved the connection with Renio and Plastino Jr., and they are both here. Plastino Jr. and Renio, where is there? Why I was interested in doing this point to here? Because of Brezin. Once again. I forgot where is Roger. Ah, yeah. Brezin again. I met with Brezin in Taiwan, Taipei, and we discussed 15 minutes about this entropy and these things. And I showed to him the formalism. And he said, but it is not normalizable, this thing. Just that, it's not normalizable. Like Volini. He said, oh, a multilinear function. So I started thinking, it's not normalizable. But then I had to decide, do I want it to be normalizable? Or I prefer it to be non-normalizable, to have no norm. I didn't know what was the correct answer. You don't know. So you say, yeah, it has no norm, but do I want it to have norm? Maybe I don't want it. Maybe the charm is not having a norm. So I hesitated some time, but then we did works with Plastino Jr. on the logistic map. And then it became obvious to me that the problem was occupancy in phase space. So I started wanting to have a norm. It took a few years, maybe 1 year, and we succeeded. And this is what we published with Renio and Plastino. This formulation has a norm, whereas that one did not have. These simple ideas that I described to you have produced an avalanche of citations. So the paper has over 3,000 citations. That one almost 500, and that one over 700. So now people tend to quote this paper and not this. If that makes you unhappy, Evaldo, you complain to Brezin. Not at all. But if you want to complain, you complain to Brezin. Because in Taipei, he told me, yeah, it's nice, but it has no norm. Now, I want to tell you more. If A and B are probabilistically independent, this means that the probability is the product of probabilities. This is the definition of independence in probability. But do you realize that it is the formula that I showed to you before? Two series bonds, it's the product. I say, the product. Graph theory came to my mind. And it gives you this. And then I see there is an extra term, and therefore this is non-additive. If you cancel k, it becomes like this. Now we see that q going to 1 is equivalent as k going to infinity. In both cases, if q goes to 1 or if k goes to infinity, this goes to 0, and it becomes Boltzmann. But k going to infinity, k, is always accompanied by the temperature, kT. If k goes to infinity, is the same like saying the temperature goes to infinity. When the temperature goes to infinity, it becomes Boltzmann. In all cases. Nice. because Fermi-Dirac statistics, Bose-Einstein statistics, and Q statistics, at very high temperature, they become Boltzmann. And this is intuitive, because at very high temperature, there is a big mess, big chaos. When there is big chaos, this is the molecular chaos hypothesis Boltzmann had in his mind. His view happens at very high temperature. Great. At very high temperature, all states are equally probable, this disappears, and we go back to Boltzmann. So now we see on a different vein why Fermi-Dirac, Bose-Einstein, Q statistics, all these, at high temperature, they become Boltzmann. But then I look at this, or at this, and I said, it's not nice. So I define, I rewrite this in this way. This is equal to this. And I say, now it is nice. Because here I have the algorithm of Boltzmann. But then this variable, I will put a name. I will call it SQ prime. And the definition of SQ prime is this. And this happens to be equal to this. And this is Rényi entropy. When I submitted the paper to the Journal of Statistical Physics, I had only one reference for the paper. This is the only time in my life I wrote a paper with only one reference. And that reference was multifractals, because of P power Q. And the two referees wrote back, oh, it's nice, but why the author does not mention Rényi entropy? So I said, what is Rényi entropy? What is that? So I went to the library, and the library of CBPF is very good. And I found the book of Rényi. And in chapter 10 or something, I opened the book, and there is this formula. I said, oh, this formula is what I call SQ prime. Exactly. So I was not inspired by Rényi. I rediscovered Rényi by rewriting what I had in a more beautiful way. So my modification in the paper was this quantity, SQ prime, is called in the literature Rényi entropy. And I put the reference of Rényi, so it appeared with two references. That's all I changed. The referee said, okay, and the editor said, okay, and it is published. So you have this, but do you remember this formula that I showed to you for the renormalization group stuff, the variable S? Look at this variable and this variable. Isn't it strange? Two things very different, and they give the same expression. Maybe it has to do with these things, putting together and putting in a beautiful way, this happens. Now, I have used half of the time about, or less, more. Maybe more than.
I will not control you.
Okay. Well, let me say the following. Simple systems versus complex systems. And I will only focus on these words. These are typically ergodic. These are typically non-ergodic. And the secret of all this is in this box. And the secret of all this is in this box. Here, the total amount of microscopic possibilities increases exponentially with n. So if you have 1 million coins, it is 2 to the power of 1 million. And another coin arrives and says, hey, multiply your possibilities by the 2 that I like. She likes head and tail. And the others say, no problem. We have 2 to the power 1 million multiplied by 2. This is a free country, no problem. So 2 to the power 2 to 1 million, 1. So there is independence, which means there is loneliness. Because independence goes together with loneliness. We like independence, I do what I want, but it happens that the others do not care. Do not care about you. You can do what you want because I don't care about you. That's independence. This is false. This is end to a power. Very different from that. Much smaller than that. So, let me show to you this slide. So if the system is of this class, you must use Boltzmann entropy because it is the logarithm of W, and the logarithm of this proportional to n, and that's okay. But if you have this class, you do not want to use, at least I do not want to use Boltzmann entropy because it's going to be proportional to logarithm of n, and I want it to be proportional to n. So you change the entropy. And for this value of Q, 1 minus 1 divided by rho, the same rho that you see here, this is proportional to n. That's okay. And another class, stretch exponential. SQ does not work. Boltzmann does not work. S delta works for this value. It is proportional to n. So our guide is we want to have an entropy proportional to n in all cases. That's a long discussion, but this is what we want. And to do that, we pay the price of changing the connection between the macroscopic entropy to the probabilities of the microscopic world. We pay the price, we change the entropy, but we do not allow the result to be non-extensive. So for having extensive entropy, we need a non-additive entropy. Here with Filippo Caruso from Italy, he was a bright student of Andrea Rappisarda and Alessandro Lucchino, we succeeded in calculating the analytical expression for Q as a function of the inverse central charge. So here you have the Ising model, here you have the XY model, this is the formula, and when you take C going to infinity, this goes to 1. So C is like a dimension, and when it goes to 0 here, this goes to Boltzmann. This is the most beautiful illustration that we have, that we are not abandoning Boltzmann. We are generalizing Boltzmann. So there you have Boltzmann. These calculations has been done from first principles, from the Hamiltonian. In fact, from the universality class of the Hamiltonian. There is no fitting, there is nothing like that. This is just straightforward calculation, and you get this result. No, not now, because I will not control you, but it looks at me.
Remember that we have a dinner today.
Yeah, we have a dinner. So let me show to you another thing. Q, through a paper that started with Angel Plastino and a Chinese colleague, and then continued with Marcelo Lira from Maceió, we arrived to this expression through Whedon-like arguments, and then this was proved for a class by Alberto Robledo later. And with this expression, it is possible to calculate Q with 1018 meaningful digits. Celia and Teneolo helped me to take this number from the computer and put it here, because it's not easy such a number. And here, this is not fitting. This is a result from this analytical expression. This because I'm tired of hearing people saying, oh, it's just fitting, just fitting, just fitting. I'm sick of that. Because it is false, profoundly false. Because if anybody is capable of obtaining 1,000 meaningful digits through fitting, he deserves half a dozen of Nobel Prizes. So this is not fitting. Here we have the Q Gaussians. Q equal 1 is a Gaussian, Q equal 2 is the Cauchy-Lorentz distribution. There is a lot to say about that. In this differential equation, I took beta equal 1, so I play with alpha and Q. Today in the morning, Sabir Umarov took Q equal 1, and he played with alpha and beta. So here you have a triangle, like the one we presented this morning. And here you have the central limit theorem, and here you have Levy things. And if you put all this together with the Q Gaussians here, you realize, I will not enter into the details, that it should be nice that, like here, you have the central limit theorem, and here you have the Levi-Legienko central limit theorem. It would be nice to have a central limit theorem here and here. It's like Mendeleev with the table. It works here, 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 and something is missing. And it's not harmonious. You say, oh, it should be there. Why it's not there? Why you say it should be there? Because of beauty. Because of beauty. You say it should be there. Then it will be beautiful. So I looked during many years for generalizing these theories, these two theories. And we succeeded with Sabir. Here you have Sabir and another pure mathematician for the central limit theorem, and here for the Levi-Legienko central limit theorem with Murray Gell-Mann as well. This as a whole structure, which makes that here you have Gaussians when Q equals 1, here you have Levy distributions. When Q is different from 1, strong correlations. Here you have Q Gaussians, and here you have Q alpha stable distribution. Because nature is plenty of Gaussians, we believe that it is due to this theorem. This theorem does not depend on details. So as soon as it satisfies a couple of hypotheses, it gives you a Gaussian. And this is why there are so many Gaussians in nature. Here, nature should be also plenty full of Q Gaussians. So we are looking for them. And I would like to present to you one that we found with my doctoral student Leo Sirto. Even if you have not done all those photos, I would still have presented this because I like it very much. By the way, there are still 4 copies here for those who want with photos that were selected and prepared by Leo. So here you have the range of the interaction, alpha, and here you have the dimension. And alpha equals z is the borderline. Whatever is here, the potential is integrable, and here it is non-integrable. So this is the region where you must use Boltzmann, and this is the region where if you can use Boltzmann, it will not describe reality. Like the drunk that was looking for the keys of his house below the light, and the friend says, "What are you doing there?" "I'm looking for the keys." "Ah, you lost them here." "No, I lost them there. But here there is light, so I'm looking here." So sometimes you can calculate Boltzmann. You can. You should. Because the keys are not here, are there in the darkness. So here you have Newtonian gravitation. D equals 3, alpha equals 1. If it wasn't that one, we shouldn't be here talking or observing. And there you have dipole-monopole, which is the tides of the sea, and there you have dipole-dipole. So I want to show to you a model here, 1 point here and 1 point here. Here, for alpha big, Boltzmann should be okay. And here, for alpha small, Boltzmann should not be okay. So let me show this to you. It is this paper that appeared 4 days ago with Leonardo and a young student, a young postdoc who is in Bahia. And look what happens. We have here kinetic temperature as a function of time. So it has things like this, and then it goes here. So I will show to you results here, where the temperature is that of Boltzmann. During 15 years, all of us were thinking that this state is a Boltzmannian state. Why? Because the temperature here is that of Boltzmann. I thought this, Andrea thought this, Alessandro thought this, Stefano Ruffo thought this. Everybody was thinking that, Celia and Teneodo, we were thinking here it is Boltzmann, because the temperature, the kinetic temperature is not the Boltzmann. But this being that of Boltzmann is necessary, but not sufficient. And in fact, it looks like Boltzmann in this plot, but it is not. And I will show you. Here, these two graphs is log linear, the distribution of velocities. Everything is the same, excepting alpha here is long-range interaction, and here it is short-range interaction. When you have short-range interactions, here you have a parabola, in the log linear, which means a Maxwellian distribution. And he recovers in the computer exactly Maxwell distribution with the temperature it should and everything. But when alpha is small, it is not Maxwellian. It is this. And the black line that you see there is a Q Gaussian at least for 5 decades. It might well be a Q Gaussian for infinite decades. Why? Because of the theorem. So, what is happening here? Let me show you here. I told you we are working on this plateau. So, we did ensemble average here, here, and here. Ensemble average. And we get a Gaussian, a Gaussian, a Gaussian. And then we did time average here. And we got a Q Gaussian. So, the system is non-ergodic. Ensemble average gives Gaussian, time average gives Q Gaussian. Which one is more important? Time average is more important. Why? Because if I do like this, you hear a sound, there are waves, etc., etc. But while my fingers are touching here, there are trillions of collisions of the molecules of my fingers with the molecules of the wood. Trillions. So what you hear is the time average of trillions of collisions. All experiments are like this. The important thing in experimental physics are time averages and not ensemble averages. And time averages do not like Boltzmann when you have long-range interactions. Let me go now to high-energy physics. I chose about 4 examples to show to you as things that are recent. Here you have the LHC, 27 kilometers of electronics. Here you have the detector, CMS. Here you have a human being. Here you have the detector. So, in a very recent paper, Wilk, who was one of the people that talked in the presentation of Antonio, he put together data from CMS, Atlas, and Alice, 3 or 4 detectors, big detectors in LHC. And they obtained this, log. These are the data. And the black line is a Q exponential. Here, 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 all these are Q exponentials. But here, it is fantastic. It's a Q exponential for 14 decades. 14 decades. Here, I was very amazed when I saw this, for 2 reasons. first of all, I said to myself, my God, how they can be so talented, these experimentalists, to measure a quantity for 14 decades. Incredible. And second, the 14 decades support a Q explanation. So, we did our work together with Leo, and we analyzed this with more details, and everything goes perfectly well. And the little oscillations that Henrik showed this morning might be related to these oscillations that we see here in these 14 decades. Might be related. And then I said to myself, I can't really understand, I can't feel 14 decades. Because I can feel 0.1, I can feel 0.01, 0.001, but 0.000000014 times 1, I don't know what to think. So I wanted to compare with something. So to compare with what? 14 decades. So I remembered the master, Einstein. So here you have in log momentum and energy. So here is Newton. The energy is p squared divided by 2m. This is Newton. And this is Einstein. This is the celebrated formula of Einstein with p equals 0 equal mc squared. The only formula that journalists, that reporters know. E equal mc squared. They think physics only that. So where Einstein departs from Newton at this point, which is 10 power 0, and here we put with Leo the extreme energy cosmic rays that are being measured right now in Argentina, in Malargüe, the Auger project. And they arrive to 10 to the power 8 tera-electron volt, a huge energy. And they use Einstein expression, this, all this way. And how many decades you have here? 11. 11. And here you have 14. So I said, my God, 14 is very much. Because Einstein expression of the energy is only checked up to 11 decades. This is checked 14 decades. I still don't understand what is 0.000001. But now I have the feeling it's a lot. Let me go to the last point I would like to show to you. Here you have a famous paper by Stephen Hawking, Black Holes and Thermodynamics, from '76. So he wrote here, the logarithm of this number, of the number of configurations, can be regarded as the entropy of the black hole. So the logarithm of W is what? Boltzmann entropy. So he says it is the entropy. He does not say it is Boltzmann entropy. He says it is the entropy, because for him there is one entropy, which is that of Boltzmann. But here, strangely enough, in the abstract, he says standard statistical mechanical canonical ensemble cannot be applied. He denies Boltzmann here. He denies Boltzmann here, and he uses Boltzmann there. Ask him why he does that. He knows that the Boltzmann weight does not work, and the Boltzmann weight comes from Boltzmann entropy, and nevertheless, very nicely, he uses Boltzmann entropy, and he sleeps at night. And then, here you have Nature, 93, all these people, several Nobel laureates, like Prof, for example, this letter, where it is written, why the entropy of a black hole is proportional to the square of its radius, and not to the cube. Why to the surface rather than to its volume? Why the entropy of a black hole is not extensive? Why this? And he's not the only one. Hawking says that, he says that. This guy is a well-known specialist in black holes, he says here the entropy scales as a lower power of the area. The area, as opposed to the volume proportionality of black hole entropy, has been an intriguing issue. He doesn't like that very much, but he sleeps at night, like Hawking. And another one, Padmanabhan, Ivan knows very well, he's an important guy in this area of physics. He writes in his paper, 2011, thus the extensive property of entropy no longer holds. And he sleeps at night. So, the idea is the following. We are not going to discuss that the logarithm of W of a black hole is proportional to the area. We are not going to discuss this because a lot of physical arguments hint this. So I say, this must be true. But then this is not. It's Boltzmann entropy, but it's not the thermodynamical entropy. So I put this question, is this quantity the thermodynamical entropy? And I suspect it is not. So, the idea was, Boltzmann doesn't work. SQ, I was trying to find the value of Q for which it worked during several years. At a certain point, I thought Ivanov had found the value of Q equal 1/2. But it was not clear, and in the Vatican, inside the Vatican, in a meeting of the Academy of Sciences of Vatican, half of the members are Nobel laureates in physics, chemistry, medicine, etc. I had nothing to do, because you can imagine inside the Vatican you don't have much to do. So I was trying to find what is the value of Q that works. And I realized that there is no value of Q that works. Therefore, SQ does not solve the problem of black holes. And then who solved the problem? And then I remembered that in a footnote, in a book that I wrote in 2009, I had introduced this. And I introduced it in a footnote because I didn't know what to do with that. So I just put it in a footnote. And that moment, Ernesto from Bahia called me by phone, and I told him, listen, I am inventing a new entropy. I don't know what is it good for, so I'm writing it in the footnote. Okay, this is the one that works for the black holes. And here, the entropy, delta equal 3/2, not Boltzmann. Boltzmann is delta equal 1. Delta equal 3/2, that one is proportional to the volume. Now, me too, I can sleep at night. Now I'm happy. So, here you have a synopsis of what I was telling you. This entropy is additive, this is non-additive, this is non-additive. If you have this class of systems, you must use that of Boltzmann, because it is extensive. And you must not use SQ and S delta. If you have this class, you must use SQ. If you have this class, you must use S delta. So if you married Boltzmann, you will stay here until the death separates you. That is the true marriage. The guy will always say, I use Boltzmann. That's it. Because when he was 19 years old, a professor said to him, the entropy is this, and wrote Boltzmann. And since then, he uses Boltzmann. And he feels uncomfortable of using anything else. So if you married Boltzmann, you will stay here forever. If you married Clausius, this is to say thermodynamics, and believe me, this is a better marriage. You will stay here. Let me comment that these confusions are all over the history of humankind. It's not the first time, it's not the last time. Look what happened 3,500 years ago. This Tutmosis became pharaoh of Egypt. And there you have Egypt, and they had very good astronomers. And the astronomers called north along the river, along the flow, and the south against the flow. The flow of what? Of the Nile, because they only knew the Nile. So this way is along the flow, that way is against the flow. But he was a very good pharaoh, and he invaded the nearby countries like Iraq, so he arrived to Euphrates. And they found the Euphrates, which goes the other way around. Instead of going to the Mediterranean Sea, here you have Cyprus, it goes the other way around, it goes to the Persian Gulf. And they became crazy. What's going on? Not only the astronomers, the soldiers, which were very ignorant, they knew that when the river goes like this, the star goes like that. And here, it was the other way around. So even the soldiers were absolutely intrigued. What is happening here? Is our religion wrong? Because the religion was that the Nile is a cosmological river. It goes into the Mediterranean Sea. From here it goes to heaven. In heaven it moves the star. And then it goes back to Black Africa and comes back again. So it was the cycle of life. So all in the universe was controlled by the Nile. And here it doesn't work. So it was a terrible problem. When they came back to Egypt, they did the obelisk for Thutmose I, and they wrote here, that strange river, that when you go along the river, along the stream, you go against the stream. What about that? When you go along the stream, you go against the stream. Why that? Because they only knew the Nile. They didn't knew the Amazon, which goes like this. And now every child knows that the flow of rivers has nothing to do with the motion of stars. Now every child knows that. But at that time they didn't know. So it was a big mystery. What is happening here? The earth, the religion is wrong. What is happening? So, because they were confusing two concepts, the flow of rivers and the motion of stars. These two concepts have nothing to do one with the other. It just happens that they only knew the Nile, and these two concepts coincide, and they were confused. Additivity has nothing to do with extensivity. It just happens they coincide for this class, and it fails for all the others. Well, there are many books about that. That one was written by Suyari, he's somewhere in the room. And there are a huge amount of articles, over 4,000 articles, written by over 6,000 scientists all over the world. How this avalanche can come from what I told you before. If you want a small probability to become powerful, put a power. That's all. Well, that's theoretical physics. Theoretical physics is like that. A little puzzle solved in a different way can change enormous amounts of perceptions on the connections between theory and experiment. But this particular could not exist if there wasn't many people that have contributed enormously in this area. And even if we are late, I cannot skip to show to you some of them, starting with Evaldo Curado. Then Ángel Plastino father and Junior, who is here. Renio Mendes, who is here. Sumiyoshi Abe from Japan. Raja Gopal from India, but he was in the United States. And he wrote to me, I'm very old, I cannot travel from India to Brazil, it's too far away, but I want to give you a gift. And this is the gift he sent to me, 26 September, Raja Gopal. This is more than a dozen of pages, plenty of complicated calculations. That's the kind of things that Rajagopal likes, and he's over 80 years old. You have Ananias. He was the first to ever publish entropy with my name. And here you have Anashame, who is in the room there, and she was the first one to ever use the expression statistics with my name. It is very pleasant, of course, to see your name in those concepts, but it is particularly pleasant when those names have been introduced by two students of yours. Here you have Marcelo Lira, here you have Fernando, here you have Ernesto Borges, who is here, here you have Andrés Souza from Sergipe, here you have Andrea Lapizarda and Alessandro Cucchino, they are sitting there. Filippo Caruso, he's not here. Lisa Borland, whom you saw. Luciano, who is here. And you see all of them are individuals. So I told Luciano, listen, I'm going to put two individuals. No, leave it as it is. Why? Because Lisa is a beautiful woman. So he wants, so why not? He wants to give the impression beautiful women like me. I made what he wanted. I leave it together. Celia Anteneoro, who is sitting here, Alberto Robledo, they have given great, all of these people that I'm quoting there, they have given great contributions to all of this theory. Here you have Peter Landsberg. He died a few years ago, very old. In his book, Thermodynamics and Statistical Mechanics, I was showing to him in Rio de Janeiro, and we were drinking an acai in San Conrado, and he told me, in the first page of all books of thermodynamics, it should be written that the book concerns short-range interactions. But it is not written. But in mine, it is written. So I checked his book, and it is written. In 78, 10 years before the paper that I published, the presence of long-range forces causes important amendments to thermodynamics, some of which are not fully investigated as yet. So this is why I'm presenting him in a big photo. Here you have Jan Naut, who is in the room. Here you have Hans Hermann, I mentioned him several times. Roger Menard, he's there. We were in Florianopolis with Roger Menard, and it came to my hands a paper by Plastino and Plastino. And they had used this entropy to discuss an astrophysical problem related to the fact that for some astrophysical systems, you cannot have simultaneously finite the energy and the entropy, and you should have them finite. So they published that paper that was the first connection to real physics. And I did not understand why it works. So with Roger Menard, we discussed in Florianopolis for hours. And then we arrived to the conclusion. It works because it is long-range interactions. This is why it works. You remember, Roger? We found this without even knowing Peter Landsberg. Here you have Piero Quarati, whom you saw talking, Gregor Wilk, again, also, Roberto Andrade, Samir Umar, he is there, Erwin is there, Miguel Fuente, he is in Chile now, Yuzuru Sato, Ugun Tirnakli, who is here, Silvio, who is here, Antonio Coniglio, he's everywhere. Guiomar, Antonio are here, Stefan Turin and Rudolf Hamel, Pier Giulio Tempesta, who composed the Tarantella that you heard, Luis Mojano, who is not here, Daniel Stariolo, he's here, Pancho Tamarit, he's not here, he's now the president of the second most important university in Brazil. Hiroki Suyari, he's here in Argentina. Hiroki Suyari, Mariela Portesi, Flavia Perini, they had done a lot of contributions, and they were students of Plastino Fada. And one day I asked the president, how come you have so beautiful students? But he's a little bit like Shana. Well, that's me. So there you have two of them, Mariela Portesi and Flavia Benini. Max Jauregui and Leo Sipro, they are now doing doctoral degree here. Veit Schwemble, Jesus de Esa, who is here, Henk Hilkhorst, who is very careful in the mathematics, and he gave two nice contributions in his field. Soares, a lot of contributions. Here you have what I call the New York team, with Thisterton, Paul Rifkin, Henrik Nelson, Thisterton is that one, this is John Marsh. Here you have Christian Beck and Eddie Cohen. Here you have Murray Gelman at the Santa Fe Institute, and there are many, many more. I just wrote some of them here, but I'm pretty sure there are people in the room that have contributed in the field and are not quoted here. I apologize. It's just very hard to remember all these names. And finally, I would like to finish that all this happens in an atmosphere of freedom. Si l'action n'a quelque splendeur de liberté, elle n'a point de grâce ni d'honneur. Montaigne. So the action has no splendor. It has no grace nor honor if it does not have some splendor of freedom. And what do you want the freedom for? For a lot of things, but for example for that. Tout le monde savait que c'était impossible. Il y avait un qui ne le savait pas. Alors il est allé et il l'a fait. Everybody knew it was impossible. There was one that didn't know. So he went there and he did it. Jean Cocteau, but it is also attributed to Marcel Pagnol, Winston Churchill, Mark Twain. It seems that the original one was Cocteau, and it's so beautiful that everybody said, I said. And finally, what I see from all this is that don't think that things are impossible, because it's very hard to be sure that something is impossible. Many people think it is impossible, and it is possible. Yesterday evening, Adrian gave an illustration of that to Roger. He made a trick with cards that Roger and myself were thinking it is impossible. But it is possible because he does it and he does it again and he does it again, so it is possible. But Roger and myself, we had I was thinking, oh my God, fortunately there are some people who do mathematics because they check the proof. Because sometimes you think it's not possible and it is possible. So Freeman Dyson is convinced that the scientific truths are so profound in our thoughts that the only certainty that we can have is that most of the things that we think will reveal to be false. When I saw this, I remember Socrates. En ida then ida. I only know that I know nothing. I must live another 70 years. Something like that. Thank you very much for all of you. You're very generous.
Thank you all. That is good.
Real,